doing it.
Yeah. No problem.
What time is now?
It's 1:05.
For post 1. Okay, maybe we can start in 1 minute. Okay. Hello, everybody. Good morning, good evening. Today we have a pleasure to have a talk by Daniele Oriti. He will tell us about group theories for quantum space-time. Please, Daniele, 1 hour.
Yeah, thanks a lot for the opportunity to give this talk. What I'm going to do is to, for a large part of my time, to introduce this specific formalism for quantum gravity called group field theories. And I will try to, first of all, give the basic intuitive idea of what these models try to do and to be. Then to convey the main points of the formalism at a slightly more precise, in a slightly more precise manner, emphasizing in particular the connection, the links to other quantum gravity approaches that you may have heard of. And then in the last part of the talk, I'll give a brief overview of some recent research directions within this approach. And in the last part in particular, I will show how we extract an effective cosmological dynamics for these models and connect to general relativity. So let me start. I first give you the intuitive idea, as promised. And in this context, although the formalism can deal with arbitrary dimension, in most of the talk, I will focus on the four-dimensional case, starting from the intuitive idea. So one possibility for approaching the problem of defining a theory of quantum space-time is to discretize, or in a fancy way of saying it, chopping it up space in building blocks. So to replace a continuum manifold and its geometry with a discrete manifold, a lattice, and the geometry, a discrete geometry associated to the lattice. So you replace the smooth metric of general relativity and the Einstein-Hilbert action governing its dynamics with some discrete counterpart. For example, you can use a lattice and a geometric assignment corresponding to a set of edge lengths for all the edges in the lattice, and the dynamics for them could be given, for example, by the so-called Regge action, which is a straightforward discrete counterpart of the Einstein-Hilbert action. This is in fact the basic idea of many lattice quantum gravity approaches that you may have heard of. You could try to define a path integral for quantum gravity on a lattice, for example, in the context of quantum Regge calculus, in which you fix a lattice, you have a sum, a dynamical sum over edge lengths assigned to the lattice, weighted by the exponential of the Regge action. And then you have to look for a continuum limit and the refinement of the lattice. A complementary way of defining the lattice path integral for gravity is given by dynamical triangulations or causal dynamical triangulations, in which you still discretize in terms of edge lengths and Regge action, but you only work with equilateral triangulations, so you fix the edge lengths to be equal, and the dynamics of geometry is encoded in a sum over all possible lattices for a given topology, all being equilateral. In these approaches, the perspective is that what you're trying to do is not really to define the quantum theory of some new type of more abstract, discrete degrees of freedom underlying space-time, but is a very conservative one. You just try to make sense of the continuum path integral through a lattice regularization. Group field theories come when you somehow take a little bit more seriously or more boldly or in a more speculative manner the same discrete building blocks, and you treat them as fundamental atomic constituents of quantum space. So you are in 4 dimensions, your spatial or boundary data are 3-dimensional lattices, and you consider them as coming from building blocks. So in a sense, you decompose, you focus on the building blocks making up a 3-dimensional lattice, and then you consider them as fundamental degrees of freedom, having their own, fundamental status. So a particular lattice then in 3D will be a specific configuration of such building blocks. So it's not a discretization of a smooth geometry or of a smooth manifold being the actual fundamental entity, but the building blocks, the discrete chunks are fundamental. They can organize themselves in a particular lattice structure. That's a particular configuration. And the idea of group field theory is that you promote this description in terms of chunks to a quantum field theory. You're going to have a quantum field theory whose quanta are such fundamental cells or building blocks. And the data associated to a single building block are going to be the geometric data for a single simplex in a lattice formulation of discrete geometry.
Sorry, Daniele, can I ask you a question here?
Yeah.
So in principle, in this picture, time could be still like continuous?
In principle, but it's not going to be.
Okay.
I'm going to speak about dynamics and the processes that these building blocks can satisfy, can undergo in a slide, basically. So just be patient. I'm getting there.
Yeah. Okay.
So the intuitive picture, I'm focusing from what we can visualize, so space, is that we are going to have a quantum field theory of the building blocks that are going to build up space-time, and it's not a quantum field theory on some particular space-time with a given geometry. So it's a quantum field theory formalist, but necessarily more abstract than what we're used to when we do, particle physics, and we have a given geometry and objects, particles living in a given space-time, on a given space-time. So what about the processes indeed? Well, indeed, you can chop up space-time as well. That itself can be given by lattice. Again, I have to visualize in 3D, but now I'm talking about how you can discretize a 4-dimensional manifold in terms of 4-dimensional lattices with their assigned geometry. And the idea in group field theory, the intuition, again, then I'm going to be a little bit more technical or precise, but again, just the intuition. The idea is that just like a particular 3-dimensional lattice is a specific possible configuration of this many-body system given by all these cells or building blocks, a 4-dimensional lattice, any given 4-dimensional lattice, is understood in the formalism, in the group field theory formalism, as a specific possible process that these atomic constituents can have as a dynamical process. In the same sense, and this is going to be more precise in a second, in which you have particles in a quantum many-body system, and the elementary processes are the Feynman graphs. So particles being created, annihilated, scattering to one another, forming an object at 1 dimension higher from the combinatorial point of view, which would be a graph, while the initial blocks are just point particles. Anyway, so we have a quantum field theory of such atomic constituents that is going to be the group field theory, and at dynamical level, what you're going to see is that the elementary processes that I just said correspond to possible lattices are going to be the possible Feynman diagrams of the field theory. And the data that we associate to such lattices are going to be geometric data for the lattice dual to a Feynman diagram of the field theory. So once more, the point is to have a quantum field theory of the space-time degrees of freedom and not on a given space-time. So let me make things a little bit more precise in a couple of slides, but let's again give a further intuitive idea of how, from a formulation of the microscopic degrees of freedom of space-time of this type, you can try to build up a space-time and have an emergent gravitational dynamics. So we are going to have building blocks that are described in whose fundamental data are going to be given in group theoretic language. And this is where the group field theory label come from. The elementary processes will correspond to the Feynman diagrams of the theory. And the Feynman amplitudes will correspond to lattice gravity path integrals. Now, how does a continuum space-time and a continuum geometry come out of such discrete structures? Well, they have to correspond to collective physics. So in the same sense in which from any quantum many-body system, an effective continuum description like a fluid comes up from the collective dynamics in an appropriate coarse-grained approximation, the same will have to be true for space-time in this picture. So you need a large number in the limit infinite degrees of freedom. And a continuum geometry will correspond to a coarse-grained description of the discrete geometry of many atomic constituents. And the dynamics of GR will have to be extracted from will have to correspond to an approximate description of such collective quantum dynamics of many quantum gravity atomic constituents. So what I'm going to talk in the last part of the talk, once I try to give more precise details about the definition of the models, is indeed to show what you have to do to extract an effective continuum gravitational description. And this has to do, like in any quantum many-body system, with renormalization group analysis. You have to have some control over the continuum phase diagram of such models. And then for in some appropriate phase, you have to extract an effective description of the dynamics to match to GR. So let me give now more details. So to make everything a little bit more concrete, hopefully the intuitive picture is there, and now we flesh it out. So let's start from the constituents themselves. The single atom of space is a quantized tetrahedron. What do I mean by that? Well, you can actually give a straightforward classical description of the geometry of a single tetrahedron with Euclidean geometry, but you can describe it also in the same setting, but in different variables. So in group theoretic variables, I make a longer story short, you can associate to a tetrahedron a phase space, which is the cotangent bundle of a group. In some particular formulations, which I'm focusing on, is just 4 copies of SU2, the rotation group. And the variables that become the phase space variables are area vectors, which are in fact isomorphic. They belong to the algebra of SU2, and elementary group elements, which you can understand as a discrete connection valued in the group SU2. Then you have to, in order to have a proper geometric interpretation, you have to impose a number of constraints. It's a result in classical Euclidean geometry that if you have 4 area vectors, they do encode the intrinsic geometry of a single tetrahedron if they are forced to lie in the same hypersurface. That's the constraint that you see in the inside the box, the first one. And then the second one is that they are also forced to close, so that the 4 surfaces associated to the 4 triangles form the boundary of a 3-cell. With this data, you can compute any geometric quantity for a single tetrahedron. Instead of saying more about that, let me make one further step. starting from that phase space classical description, you can quantize, for example, by geometric quantization, and the Hilbert space associated to a single tetrahedron at the quantum level will be basically a direct sum over Hilbert spaces associated with representations of SU2, one for each triangle of the tetrahedron. And each representation space is contracted with an intertwiner space, so with an invariant tensor in the representation space. And that's the closure condition that I was mentioning. Now, I'm not going to give more details here unless you ask. The point is that even at this quantum level, which is, as you can see, a purely algebraic description of the data associated to a quantum tetrahedron, you can see the action of geometric operators quantized, so the area, the volume of the tetrahedron, and others. And you see that the representation labels of SU2 give you indeed the spectrum of the 4 areas for the 4 triangles. And the intertwiner label gives you the spectrum of the volume operator. Now, you have to take my word for it here. I'm not giving you the derivation, but this is just an extra piece of information to convey the idea that the geometry of the single tetrahedron at the quantum level is encoded in the states forming such Hilbert space. For the same Hilbert space, you can have equivalent representations. In particular, you can go from a representation in which the quantum states are labeled by representations of SU2 spins, basically the ones I just mentioned, to a representation in which you have group elements determining a basis for the Hilbert space. And this is the same as a sort of a Fourier transform, is the Peter-Weyl decomposition for functions of SU2, is a bit like a Fourier transform from the configuration space, which were the group elements in the classical description, to the momentum space, the conjugate variables, which are the reducible representations of SU2, the spins. Then you can, let me mention that you can have equivalent geometry descriptions that use the full Lorentz data, and there will be group field theory models that instead of using SU2 use the full Lorentz group, but the basic story is the same. It's just the specific model building that works differently. Then the idea of going to a field theory is, as usual, to promote the single quantum wave function to a field. So you get a field over 4 copies of SU2 group manifold, which SU2 is a Lie group, so it's a differentiable manifold with a metric, a topology, and so on. So you can define a field theory over it. In case you were wondering, so far I've been talking just about a single tetrahedron. You can, of course, start gluing tetrahedra together to form extended structures. And interestingly, the gluing, again, I'm not going to give many details here, I only want to give an introduction, but interestingly, the gluing of 2 tetrahedra to form an extended lattice made of 2 tetrahedra, indeed, corresponds to a state in the tensor product of the Hilbert spaces of 2 tetrahedra, which is maximally entangled. So the connectivity is indeed entanglement, is given by the entanglement in the corresponding tensor product Hilbert space. And so you can construct extended simplicial complexes in 3 dimensions by gluing together tetrahedra and focusing on, therefore, on entangled states. So maximally entangled states with appropriate entanglement pattern correspond, admit a coherent interpretation as connected simplicial complexes. In fact, you can say a little bit more here. You can even ask, whether the geometric operators I discussed earlier, the area of the triangles, the volume of the individual tetrahedra, have an interpretation in terms of entanglement. And the answer is yes. In fact, there is a sort of a primitive entanglement geometry correspondence at the level of simplicial geometry, with the measure of entanglement across two tetrahedra scales with the area of the triangle shared by the two tetrahedra. The volume of an individual tetrahedron measures the entanglement of the four representation spaces incident to the same, corresponding to the same tetrahedron. Okay, anyway, this is just to say that from a single tetrahedron, you can go to many tetrahedra, and in fact, all these states can be embedded into a Fock space whose one-body Hilbert space is that of a single tetrahedron. So you really have a Fock space of quantum tetrahedra, and I'm assuming here and in the following bosonic statistics. So you can introduce the field operators, so creation and annihilation operators that allow you to move around this Fock space, and they create and annihilate tetrahedra, quantum tetrahedra. And you can promote the geometric operators you had in a first quantized picture to a second quantized picture. For example, the total volume operator for a many-body state corresponding to many tetrahedra is simply the sum of the contributions to the total volume from the volume of each of the tetrahedra. Okay, just a note of caution here, I'm talking about geometry, but I'm only talking about geometry in the context of discrete lattice geometry. Moreover, a generic state in such a Fock space will not correspond to a connected simplicial lattice, and definitely will not correspond to anything resembling a classical simplicial geometry. So not only you have a lot of states that do not admit the interpretation of a connected simplicial complex, so purely in a topological sense, but also even when they do, their geometry will be highly non-classical. There's no reason that they will peak on a specific phase space points for the classical geometry of a bunch of tetrahedra. Okay, let me at this point emphasize the connection to the canonical loop quantum gravity approach. This quantum tetrahedra admit an equivalent description in terms of so-called spin networks, which are the quantum states found by the canonical loop quantum gravity approach, starting from a straightforward quantization of general relativity. However, they are organized in this context in a different manner within the Fock space, and in particular, when you superpose different graphs, you see differences between the canonical loop quantum gravity Hilbert space and the group field theory Hilbert space, which is the Fock space. But clearly, you can think, at least intuitively, but you can make it more concrete, of group field theory for appropriate models as a sort of a second quantized reformulation of canonical loop quantum gravity. If you know about that and you come from that perspective, that's one way to understand the group field theory formalism. Let me move on, and let me talk about the dynamics. And first of all, explain what I said at the beginning, this intuitive idea of elementary processes in group field theory corresponding to simplicial lattices in one dimension higher. So dynamics here will be discrete dynamics in terms of discrete geometry and discrete spacetimes. So, of course, I don't have to recall how, Feynmanology works for point particles and local quantum field theories. Your quanta are point particles, zero-dimensional objects. Your processes are one-dimensional objects, which are the Feynman graphs. And having a given local action for your quantum fields of point particles, then you can deduce what the elementary propagator is, what the elementary vertex is, and you can put them together to give a quantum amplitude to each elementary process that is a Feynman amplitude. If you know about matrix models, then you know already that all of this story can be generalized from a combinatorial point of view, and you can consider, instead of point particles, you can consider one-dimensional objects represented as segments with two endpoints, each labeled by an index. and your dynamical field is in fact a matrix that you can take to be of finite dimension. Then the combinatorics is generalized because you have to keep track of the two indices at the two endpoints of the segments. And if you write the models appropriately, your Feynman diagrams, keeping track of how the indices are rerouted in each interaction vertex, your Feynman diagrams will be dual to two-dimensional simplicial complexes for appropriately constructed models. So you're going to have vertices of interaction that instead of being one simplices, that is your segments, are two simplices, that is triangles. And they're glued together through the propagators. The same idea, you can generalize it to higher dimensions in the form of so-called random tensor models. Instead of a matrix, you now have a tensor, and this is the three-dimensional case. So it's a rank 3 tensor of finite dimension for each index. So it's an n by n by n tensor. Instead of depicting the fundamental entities as segments, now they are themselves triangles with the three edges labeled by the three indices of the tensor. And the combinatorics of the Feynman diagrams, and even before that, the combinatorics of the elementary vertices of interaction and the elementary propagators across interactions between different interaction vertices, generalize it. So the simplest interaction vertex you can write down will correspond to 4 triangles, so 4 tensors, which are combined, traced across indices to match the combinatorics of 4 triangles glued along shared edges. And that is in the action at the bottom of the slide. A Feynman diagram here, of course, will have a more complicated structure because you have to keep track of the 3 indices along every propagator and inside each interaction vertex. But by construction, it will be dual to a 3-dimensional simplicial complex, something that corresponds to tetrahedra, being the interaction vertices, glued together. Then the combinatorial generalization to arbitrary dimension follows the same logic. You have 4 tensors, so 5 tensors depending on the dimensionality. If you go back to what I was saying about the fundamental fields of group field theory, in the 4-dimensional case, you realize that we have exactly that. We have a field over 4 copies of a Lie group that was SU2. So it's a 4 tensor with the richer Lie algebra and Lie group data that made the indices taking value not from a finite set, but from a Lie group or the corresponding representation space. But the combinatorics of the elementary processes is just like in the random tensor models that I mentioned. So the 4-dimensional Feynman diagrams of 4-dimensional group field theories will be dual to 4-dimensional simplicial complexes. And let me emphasize that because these complexes are generated as Feynman diagrams obtained by gluing together in all possible ways the simplices of the appropriate dimension, you get a sum over all possible simplicial topologies, which you have to learn to control. And this is what I can tell you more about how we learned to control such sum over topologies. Anyway, so the basic point is that for a field that defines, that corresponds to quantized tetrahedra, the Feynman diagrams will correspond to 4-dimensional simplicial complexes. To these complexes, the field theory for any specific model will associate an amplitude, a Feynman amplitude. Now, this Feynman amplitude can be understood. In fact, it can be written explicitly as a lattice gravity path integral for the lattice, for the simplicial lattice corresponding to the Feynman diagram, and with an amplitude that can be recognized to come from a particular discretization of gravity in 4 dimensions in group theoretic variables. And again, to close this part, let me mention the connection to another approach to quantum gravity that you may have heard of, so-called spin-foam models. Well, and I'll be brief here because it's not so important.
Daniele,
Yeah.
can I ask you a question before this?
Yeah, can I first say this about the
Sure.
spin-foam models, and then I can answer a bunch of questions. So just to conclude the story, I said that you have Feynman amplitudes coming from any given group field theory model, and so you choose a specific dynamics for your quantum tetrahedra, and that will give you, of course, a particular Feynman amplitude. I mean, a set of Feynman amplitudes, one for each possible Feynman diagram. And the general statement that I'll just make, of course, without proving, is that for any given group field theory model, the Feynman amplitudes will be recognized as a particular spin-foam model or a particular lattice definition of a lattice gravity path integral in group theoretic variables. And the correspondence is really one-to-one. You can also start the other way around. Take your favorite spin-foam model or lattice gravity path integral, and you can rewrite it as coming from convoluting the propagator and the vertex of a particular group field theory model. Okay, sorry. Yeah, that.
Yeah.
Go ahead.
I had a question regarding this, let's say, correspondence with the Feynman diagrams. But usually, I mean, in standard quantum field theory, continuous quantum field theory,
yeah,
when we speak about Feynman diagram, we have in mind some type of perturbation theory of our path integral.
Yeah, that's you're right. I should have emphasized. They arise from the perturbative expansion in the coupling constants that appear in your group field theory action. So it only corresponds to the perturbative sector of the field theory.
So also in group field theory, you work perturbatively?
Well, also in group field theory, you can also work perturbatively. And in this perturbative treatment, you will see the connection to lattice gravity and spin-foam models. Then you can also work non-perturbatively, like you can do in other quantum field theories. And at that level, you don't directly see the connection with lattices and spin foams.
Mm-hmm. So your approach, you are working perturbatively at this moment, this stage, right?
At this stage in the talk.
Yeah. Okay.
Yes.
I see.
As I will show you, I mean, later on when we extract the cosmology, although we do assume that the couplings are small, we don't expand the partition function in perturbation theory. We take a different type of approximation of the dynamics.
Okay, I see.
But so the main point here is the following. You have a quantum field theory that when you look at its perturbative sector, you see that the quanta have this, the states have this representation in terms of tetrahedra glued together, quantum tetrahedra glued together. When you look at the elementary processes in perturbation theory, they look like lattices weighted by a spin-foam model or a lattice gravity path integral. Then, of course, you have the field theory. So in principle, you can study the partition function in a non-perturbative manner. You don't need to expand it perturbatively. You have a bunch of couplings, and as far as you know, they could even be large.
Mm-hmm.
And then, of course, you have to use other approximation methods.
Okay.
Okay.
Yes. May I ask a question? If you have only this first term, then it is exactly solvable model, yes?
Well, if you have a free theory, yes.
Then it is a simple solvable model. What is the difference between what is the specific point when you use for any group? It is can be solved for any group, yes?
Yeah, I would get that for non-compact groups. You have to be a little bit careful, but yes, if you have a free field theory, it's it's a solvable model.
Uh-huh.
Yeah, the problem, of course, is the moment your quantum field theories is interacting, right?
Yes.
So I mean, if you're asking just from a mathematical point of view and not directly, not now about the physical interpretation, yes, I write down a field theory. The peculiarity of the field theory compared to standard local field theory is, in fact, only in the interaction part, from a mathematical point of view, because you need this combinatorial structure to interpret the processes in terms of simplicial lattices. The free part, the kinetic term, is local, and so you just have a standard quantum field theory on a particular domain, which happens to be a Lie group, which of course, in fact, is even helpful because you have additional symmetries and that you can use. But it's really a it's a field theory of no particular difficulty because it's a local field theory on a group manifold.
Thank you.
Welcome. Okay, so I hope that this this general part, at least about the structure of the models, is clear. I give you now a couple of concrete examples so that you can see specific models a little bit more fleshed out. Let me introduce for you the Bulatov model. It's in fact very old. It's from 30 years ago. Introduced by Bulatov in 91 or 92, I think. So so it's a model for three-dimensional Euclidean gravity. So it's not the four-dimensional setting that I was discussing earlier, but it's simple enough to see all the main ingredients. So this is the action. So you have a complex field over 3 copies of SU2. And it describes quantized Euclidean triangles. So the quanta are two-dimensional simplices, which are the triangles, whose geometry is encoded in SU2 data. It's subject to an invariance, which is this invariance written on the third line, is a closure condition for the triangle edges. And the action is the one you see. So there is a local and, in fact, absolutely trivial kinetic term, is something like a simple mass term for the field. And then there is an interaction that, there should be a coupling there, not one. There is some coupling constant. And then the interaction corresponds to the combinatorics of 4 triangles, each labeled by 3 group elements, with the edges identified, so that there is a convolution over the same group element for 2 triangles sharing the same edge. And the combinatorics is that of a tetrahedron. So you have Feynman diagrams, which appear, of course, in the perturbative expansion with respect to your coupling lambda, the one that I forgot to write in the formula. And what happens if you look explicitly at the Feynman diagrams is that they are 3-dimensional simplicial complexes. And when you look at the amplitudes that this model, this specific choice of action, so vertex, kernel, and propagator, associate to the Feynman diagrams, these amplitudes take different forms depending on the variables you use. Just like in ordinary quantum field theory, you can write your Feynman amplitudes in momentum space or in position space or in any other combination of variables. And what happens here, of course, I didn't report the calculation, but the amplitude that you find in the perturbative expansion, if you write it only in group variables, takes the form of a lattice gauge theory formulation of 3D gravity, which is the same as topological BF theory in 3 dimensions. And in fact, you see that you impose a flatness of the holonomy of a connection for each phase in your, for each loop, basically in your Feynman diagram. If you write it in spins, so in irreducible representations of SU2, what you find is the Feynman amplitude taking the form of the so-called Ponzano-Regge spin-form model, which is the second equality there. If you write it in a more complicated language in terms of the algebra elements for the group, which I didn't discuss, but you can show that the same amplitudes take the form of what is a discrete path integral for three-dimensional gravity corresponding to the Palatini formulation. So all these are equalities, so there's no approximation here. This is literally the Feynman amplitude being equal to the lattice path integral for a particular discretization of 3D gravity, or in different variables to a particular spin-foam model for three-dimensional quantum gravity. So this is one example of a model that realizes explicitly what I said at the general level earlier. Now, I'm not going to do the same discussion for four-dimensional models because they are more complicated, but just to give you a hint of how they're constructed. So this is a particular model in 4D based on SU2, but also using SL2C Lorentz data. So it's, I don't want, I mean, this is just to scare people. It's just that, there is a kinetic term and there is a vertex term in which you also convolute or trace over shared data for the 5 fields now entering your interaction. There are 5 because your field now corresponds to a tetrahedron, and in a 4-dimensional lattice, the fundamental building blocks of a 4-dimensional lattice, so the interaction vertices, correspond to 4 simplices whose boundary is given by 5 tetrahedra. So for each of them, you have a field, and you have to convolute the field arguments appropriately to have a proper geometric interpretation. You can also work with a different model that only uses SL2C data, and I'm not going to tell you anything about the Feynman amplitudes. They are a rather complicated structure, but what I said earlier at the general level, in terms of the correspondence between the Feynman amplitudes and simplicial gravity path integrals or spin-foam models remains true also in this 4-dimensional case with a little bit more work. So that message is the only thing you have to remember for this. And the first model corresponding to the action at the top of the slide is in fact the one I will use later on, again, without giving much details, to extract an effective cosmological dynamics. Okay, a very brief note before I talk about the more recent research developments and some results, and I conclude the introduction to the general formalism. In the literature, you will find reference to random tensor models, which I also mentioned already. You will find tensorial field theories, you will find group field theories, and you will find tensorial group field theories. I would say that they are basically part of the same class of models, and whose ingredients are basic ingredients are what I said. So that the basic object is a tensor, the basic dynamical field is a tensor, and the interactions are combinatorially non-local, so to produce simplicial complexes as Feynman diagrams. Then, depending on which specific ingredient you focus on in the construction of the model, what type of domain for the tensor, what type of symmetries, what type of action, and what specific combinatorics, then you can choose one or the other name. And I'll skip that because I only have, I think, 15 minutes. So I'll try to hurry up. So in fact, you can I would simply call everything tensorial group field theory, and then group field theory is the label I use for models with the specific quantum geometric ingredients that I discussed earlier. Okay, so to conclude, I've given you a bit of information about the general formalism, and I mentioned a bunch of connections with other quantum gravity formalism, which I think is interesting because it allows a bit of a cross fertilization, so to speak, between these models. Okay, now you have a class of field theories. You can focus on a specific model because you find it more promising or more geometrically compelling or simply mathematically more interesting. What do you do with it? Well, first of all, I justified the quantum gravity interpretation of these models in terms of perturbation theory, using the specific form of the Feynman amplitudes, the Feynman diagrams you generate, and the connection to lattice gravity. So the first question is whether this perturbative expansion is well defined. And the second question, of course, is whether you can tame the construction ambiguities that are necessarily there whenever you write down a specific model which connects to lattice gravity. There are a number of ambiguities in how you define the discretization, a bunch of quantization ambiguities like operator ordering, and so on. So this is why a lot of people are studying perturbative renormalizability, because it's a way to ensure this quantum consistency of the model. But then, of course, we know that we want to go beyond perturbation theory, and we want to study the regime of the quantum dynamics of such models in which many of the candidate fundamental degrees of freedom are interacting. And the moment you start working with many degrees of freedom, what you expect is that there will be different phases, there will be phase transitions. And so you have to be able to say which ones of these continuum phases made of corresponding to the dynamics of many degrees of freedom are somehow geometric, in which one of them you have a good approximation in terms of a smooth space-time and possibly general relativity. And this is why people also study the non-perturbative renormalization group flow of the same quantum field theories given by group field theories. And what I want to emphasize is that this story about studying the non-perturbative RG flow of group field theory is also a way to address the problem of what is the continuum limit of the lattice gravity path integrals that correspond to the same models. So the typical problem in lattice gravity, in lattice quantum gravity, which is to refine the lattice, studying the Cos-graining, the effective continuum phase diagram, and so on, it here translated in the problem of studying the RG flow of a quantum field theory corresponding to that lattice gravity path integral. And that gives a number of other tools and strategies to address the same issues. Okay, I'll just say here, before I move to the cosmology part for the last 10 minutes, I will just say that you can take advantage of the fact that despite the more abstract quantum gravity interpretation, from the formal point of view, these field theories are reasonably standard. So the interactions are weirdly non-local, but you still have a field over a differentiable manifold, which is your Lie group. So you can take advantage in particular of the structure of such group manifolds, for example, the metric, to define a scale, a notional scale that can be used for the renormalization group analysis. What you have to be very careful with is to not mistake the scale that you use in this more abstract RG flow in terms of quantum gravity degrees of freedom directly with any distance or energy scale in space-time from a gravitational point of view, because it's a different type of structures that you're using. This is not, again, a field theory on a space-time manifold. Is a field theory from a formal point of view on a group manifold whose degrees of freedom are supposed to build up space-time in some approximation. Instead of saying more about this renormalization group analysis, unless you want to know, and giving you a bit of interpretation of what you do in the RG analysis and an overview of the results, instead of doing that, I will only say that we know a lot about models in this formalism that are perturbatively renormalizable to all orders, so that we know that these field theories can be made sense as quantum field theories. We have a bunch of results also for the more complicated models, and there has been a lot of work also on the non-perturbative RG analysis of these models. And if you want, I can tell you more, but I want to rather connect to gravitational dynamics from this more abstract setup, so that you don't come out of the talk with the impression that, okay, there is a lot of complicated mathematics, a bit abstract concepts, and compelling, at best, intuitive idea, but at the end of the day, we don't know if this connects to gravity in any way. Let me show you what we know about the connection to gravity. So it's clear that we are in a context in which space-time and geometry are emergent. And this resonates with a bunch of other quantum gravity-related contexts, which is good. And as I already anticipated, we expect a continuum geometry to arise from coarse-graining the discrete description corresponding to the perturbative analysis of proof field theories, and the general relativistic dynamics to correspond to some approximate rewriting of the collective quantum dynamics of those degrees of freedom. So the problem of extracting such effective continuum dynamics is in fact very similar to the typical problem in quantum many-body physics. You know the microscopic degrees of freedom, but you need to control many of them, and you need to do appropriate coarse-graining and some other approximation methods to get an effective description. And cosmology in particular is expected to correspond to the most coarse-grained dynamics, the one in which you basically look only at global observables from the full theory. And that is basically the idea of looking at the hydrodynamic approximation of these quantum gravity models. So this is what we do. The strategy is based on an hypothesis, which is that the universe is a sort of a quantum fluid whose elementary atoms are this quantized tetrahedra, the GFT quanta. So under this hypothesis, following this hypothesis, we extract some approximate hydrodynamic equation for a fluid made out of such building blocks. We then compute cosmological observables guided by the discrete geometric interpretation of the atomic constituents. And then we translate the hydrodynamic equations into equations for such cosmological observables. And then we have to compare these effective equations for cosmological observables, for example, the volume of the universe, or equivalently the scale factor, with a relativistic cosmology, to see if we get a match with GR, in what regime, what else we get, and so on. So we start from the models in this group field theory language that I introduced earlier. The simplest approximation to the full continuum hydrodynamic description is the simplest approximation to the full quantum effective action. And that is just mean field hydrodynamics, which basically correspond to looking directly at the classical action for your preferred group field theory model. This corresponds to work with very simple condensate states, which are coherent states of the fundamental field. And we expect this to be obviously only valid in some very special approximation. The interactions shouldn't be too big, otherwise you don't expect this mean field to be valid, this mean field approximation to be valid. Interaction, therefore, have to be reasonably small. They grow with the density, so you cannot have too large density of the fluid, so too large modulus of your mean field. On the other hand, they cannot be too small either, because small densities will correspond to small number of quanta, and then you really don't expect a good continuum approximation for your geometry. So let me tell you what we do. So we try to express the dynamics in terms of some geometric quantities to be compared with the continuum geometric quantities. In order to have a comparison which is diffeomorphism invariant, we adopt a so-called relational strategy, in which you use appropriate matter degrees of freedom to define for you what you mean by a point or a temporal evolution. Therefore, you have to extend a bit the models that I introduced earlier to include degrees of freedom that at the level of discrete lattice gravity correspond to discretized scalar fields. But then we are going to deal with them at the effective aerodynamic level. These extra degrees of freedom basically enter as additional real directions, giving arguments extending the domain of your fundamental field. Are you still with me?
Yes, yes.
Okay, good.
Everything is fine.
Please
Okay.
continue.
Okay. So what do we find? So there are two general facts that for group field theory models with the type of geometric interpretation that I discussed. The first general fact is that if you look at the domain of your mean field, the one for which you get effective hydrodynamic equations, the domain of the field is isomorphic to, in fact, diffeomorphic to mini superspace for GR. So it's the space of homogeneous continuum geometries. So your dynamical variable is going to be a function over mini superspace. Just like in quantum cosmology, you have a wave function for the whole universe on mini superspace, on the space of homogeneous geometries. The second general fact is that because the dynamics for such mean field corresponds to the hydrodynamics of the fundamental theory, it's going to be nonlinear. In fact, it corresponds to the classical equations of motion of the model we started from. So what you get is basically a nonlinear extension of what you would get in quantum cosmology. From the first point, you made the connection to quantum cosmology in the sense that you have a function, a wave function, on mini superspace as the dynamical variable of your equation. In quantum cosmology, you have a Wheeler-de Wit equation acting on it, which is a linear operator acting on the wave function. Here, what you get is a nonlinear equation satisfied by the wave function, including self-interactions. And this is not surprising. It's hydrodynamics, and specifically, it corresponds to a Gross-Pitaevsky type approximation for the dynamics of your condensate of quantum tetrahedra. So the idea is to extract cosmology from the quantum gravity hydrodynamics that takes the form of a nonlinear extension of quantum cosmology. So, and this is derived, I mean, it's not a postulate. I mean, under this approximation that I discussed, four models which are appropriately quantum geometric. So they have this geometric interpretation in terms of quantized tetrahedra. This is what the hydrodynamics look like. A nonlinear extension of quantum cosmology. A nonlinear equation for a function on mini superspace. Then you want to translate this equation in terms of an equation for observables. So in the same type of condensate states, you do the following. You take the volume operator that you remember I introduced at the very beginning, summing the volume contribution from all the quantum tetrahedra. But you take it in a condensate in which some of your scalar fields, so you remember the discretized scalar fields, are picking on a particular value. And basically you choose one scalar field to be a clock and maybe other scalar field to be rods. So to give a notion of temporal direction and spatial directions. So you translate now the equation for the condensate wave function into an equation, for example, for such volume. You can do the explicit analysis once you give me a specific model. You can take the two models for four-dimensional quantum gravity I gave you the action for earlier on. And I just tell you what we find. We find that at very early times, this corresponds, the time means very small values of your clock field. At very early times, you also have small volumes, but the volume never goes to zero. It remains positive at all times. And so what you get is effectively a bounce scenario. So there's no Big Bang singularity. Then you follow the evolution of the volume observable in clock time, and you see that the volume grows. When the volume grows enough, but the interactions of the fundamental model are still subdominant, what you find is a classical Friedman dynamics for the volume, written in, and this is the equation for the Friedman equations, written in relational language. So in terms of a scalar field used as a clock. Specifically, we find flat FRW. At later times, for a class of models, we have to make some additional approximations. We find that it's quite natural to get the moment the quantum gravity interactions between the fundamental quanta, the quantum tetrahedra, become non-negligible and in fact start dominating, we find an accelerated expansion for the volume. And in fact, it looks like a phantom-like dark energy. So it crosses the phantom barrier. It's like having an effective equational state that goes below -1, but then it goes asymptotically to a de Sitter universe. So this is general. Then there are many results obtained in this context, which I'm happy to tell you more about, including going to anisotropic configurations, and even more interesting, maybe studying cosmological perturbations. So I'm happy to tell you more about that, but the last thing I want to say in my last minute, I hope I have just 1 minute, so I said that in these models, we have to study phase transitions, and we assume to extract cosmology there is a condensation transition, and this of course have to be studied much more. But I've also told you that in this condensate phase assumed to be there, and in a hydrodynamic approximation we find a bounce rather than a singularity, and this is true, and it's very nice, in my opinion, that we find it as a result from the full theory rather than in a quantum cosmology toy model. But clearly, we obtain that in a particular sector of the full theory and in a particular approximation, as I said, the hydrodynamic approximation within a condensate phase. Moreover, in a mean field restriction. If the mean field approximation can be shown to be stable, if after improvement, then yes, you can be more confident that there is a cosmic quantum bounce replacing the cosmological singularity. But you're still assuming that you can work at the hydrodynamic level and that you are within a condensate phase. If the hydrodynamic approximation instead turns out to break down in the regime in which you see a bounce, then what you have as a resolution of the cosmological singularity will not be a bounce, will be something more radical, will be that the very notion of a continuum space-time breaks down, because you don't trust this effective continuum description anymore. You have to resort to the full quantum gravity formalism. And it may even be that you are in fact approaching a phase transition of the underlying quantum gravity model. And this is a sort of scenario that people will call geometrogenesis in reverse, because you will go from a geometric phase, the condensate one, to some other phase with no geometric interpretation at all. Anyway, I leave you with this speculation, and I thank you for your attention.
Okay, thank you for your interesting talk. Thank you. Questions, please. Question, please. So I guess your suggestion is so unusual so that the people afraid ask you some questions. Who is the
Maybe I ask some questions.
Okay, please.
Hi, Daniele. It's Gaetano.
Hi.
Hi. You just mentioned scalar matter field. What about fermions? Can you put fermions and how?
Yeah, they've been put in at two
And
levels.
also other fields with a higher spin. I mean,
Okay. So, for what I know, people have included fermions. I'm not so sure they studied higher spins. They included, spin 1/2 fields. I'm not sure about higher spins, but and they have included the gauge fields, so spin 1 objects. So they've not been used in a cosmological application, so we don't know how they change the effective, cosmological dynamics that I discussed. The way they've been studied is by basically complicating the pure gravity models. Sorry?
No, it was not me. I don't know.
Okay, sorry.
It was some
Noise.
Okay, sorry.
some noise.
What they did was to look at how fermions should be, or gauge fields should be coupled at the lattice gravity level, and then construct the corresponding group field theory model. I told you that there is this one-to-one correspondence between, you take a lattice gravity formulation for any given simplicial lattice. You put your discrete geometric data. You can also put fermionic degrees of freedom. You can put the gauge field degrees of freedom as well, discretized. Then you take that and you reinterpret it as the Feynman amplitude of a group field theory. And then you write down what is the corresponding group field theory. So at this level, there's been work. What people have not done is to check what is the effective cosmological dynamics or some other renormalization analysis of these more complicated models.
Okay, thank you.
You're welcome.
Okay, there are two more questions. Please, Nikolaos Karogerapoulos. Please, Nikolaos, ask your question.
Thank you very much for the talk. Since nobody was asking any questions, or at least there is Professor Vedenyapin who wants to ask something. I said, okay, usually I wouldn't ask this, but I have a standard question that I ask to all people doing quantum gravity approaches based on triangulations or on discrete objects. As you know, there is a very substantial amount of work in pure mathematics, in combinatorial topology and stuff like this, which is associated with this Hauptmehrwertung, the big conjecture and so on. What is triangulable, what is not, and so on. And most of the people, of course, working in different approaches of quantum gravity, they ignore this. So the question is basically over what are you summing in a sort of even continuum path integral. And yes, there are some pretty nasty structures over there, which do not obviously have a continuum or even a manifold-like approach and so on. So my first question, very briefly, is the people working in group field theory, so far as you know, have they looked into this? It's not really going to be very physical in the sense that a typical physicist does not have the tools to deal with these things, because these are abstractions, global abstractions in the geometric topology and stuff like that. But it may dominate, or it may be non-measurable. It is something super nasty that somehow has to be controlled, right?
Of course. So let me answer the question at two levels. I tell you the two type of works that has been done, the two type of research that has been done in this context. So where do these simplicial complexes, including very pathological ones, can arise? They arise in this perturbative expansion of this group field theory. You sum over all possible ways of gluing together things. That was already in principle the case in matrix models, and the moment people try to generalize to tensor models, the idea of tensor models was there already in the very early 90s and didn't really go much beyond the idea, because they couldn't find a way to control this sum. And so it's exactly the problem you were mentioning. First of all, in fact, the problem is even worse, because it's not just that you find pathological topologies and then they may dominate. The problem is worse. If I just give you the sum, you don't even know how to detect what type of topologies you have inside. I mean, you don't know. Now, a lot of progress has been, first of all, done for simpler models. The one in which you have this random tensor structure, the same type of combinatorics generated as a Feynman expansion, but you don't care about adding additional group elements, additional geometric data, because you want to focus on the combinatorial issues. What has been found there is that there exists a large N expansion. So you can take a larger expansion and you can control. No, let me take a step back. Even before you take a larger expansion, you can control exactly what type of topologies you are generating using tools from so-called crystallization theory. And basically, there is a general fact that if you have a D+1 colored graph, that's in one-to-one correspondence with a simplicial pseudo-manifold in D dimensions. Now, a pseudo-manifold is, of course, more general than a manifold, but it's a very mild type of generalization because it only has conical singularities, so just point-like singularities. So people basically wrote down the old formalism that I discussed. I didn't saying anything about this not to complicate the story, but you can write it by adding additional colors, so-called, to the models, to the fields and so on, to make sure that you have a colored model that only generates Feynman diagrams which correspond to colored graphs, and therefore correspond only to pseudo-manifolds. Just by doing this mild generalization, you exclude by construction anything that is more pathological than a pseudo-manifold. Once you do that, people have studied what happens in a large N approximation. And a large N approximation means the domain of your tensor, even if it is a Lie group or a representation space of a group, whatever it is exactly the domain, the moment it goes large, what people have shown that there is a dominance of spheres, trivial topology. That is really peculiar with respect to matrix models, because you don't get all spheres. You get a particular class of triangulations of the spheres, which they may be pathological from a geometric point of view because they're sort of tree-like, but at least from a topological point of view, they are totally under control. And then they studied double scaling, triple scaling, to generalize a little bit. I don't want to say that things are totally under control, but at least we now have a lot of tools to make sense of that perturbative sum. The second strategy, in a sense, is what I said about in the last part about the cosmology thing, because at the end, what we want to extract is some effective continuum dynamics and a continuum geometric description. And that doesn't have to come from the individual Feynman diagrams being, well-defined triangulations. Just like in a path integral, you want the collective dynamics to be well-defined in some approximation, not the individual histories. And that's what I've shown. So we are trying to look directly at the hydrodynamic approximation of the full thing, so somehow resumming the whole perturbative series in a particular approximation, showing that it matches GR or in some limit. And indirectly is a way also to tackle the issue of these complicated topological structures. You just try to look directly at the collective behavior of those structures, and not at their individual properties.
Right. Thank you very much, sir. Thank you.
Yeah, well, it's a very long answer for a short question. But
but it's something that bothers all the people doing triangulations, or it's not just only the group field theory. Same thing appears in
and we've been bothered as well. That's why a lot of work has gone into try to to control all of that.
Right. Thank you, sir.
You're welcome.
Okay, the next question from Victor Vedenyapin. Victor, please ask your question.
Thank you so much for your interesting lecture.
Thank you.
My question is the following. Can you tell us kindly concerning these cosmological solutions, when do you think this group theory can be worked, and even for what group, I should say, in more concrete way even?
Okay, so I answered the second question first. So which group? So what is essential in these cosmological applications is that you have a good geometry interpretation for the domain of your mean field. And remember, it's one of the things that I said, you know, you put for a class of models for which you have an interpretation in terms of geometric tetrahedra for the building blocks, you can show that the mean field, so the hydrodynamic variable, has a domain which is isomorphic to the space of homogeneous geometries, so that you have under control how you could understand the effective dynamics and the observables you compute in this effective dynamics. For this to be true, the microscopic theory should really have either SU2 or the Lorentz group, or in the Euclidean signature, the rotation group in 4 dimensions as the basic data. Because it thanks to this type of data that you have a good description of the discrete geometry of tetrahedra. I don't exclude that there could be other choices of different ways of parametrizing or describing the geometry of simplicial structures. If you find another one, that will also be a good choice for the domain of the field in this group field theory picture. But it's essential, you cannot choose anything. I mean, you choose something for which you can deduce the geometry of the simplicial structures. Otherwise, you wouldn't know how to interpret what you do even at the effective continuum level. So that was the second question. The first one was what do we do with this? What do we want to do with these models? If I remember, this cosmological level.
Cosmological situation.
Well, I told you that yeah, I gave you an example, which is
Sir, I asked you a question.
Okay. Is it the same question? It's another question? It's an interference?
Yes.
Okay, so to start with, I've told you that we get an effective dynamics, for example, for the scale factor, for the volume. We get a generalized equation for the volume of the universe in this cosmological approximation. So we get exactly what you try to get from quantum cosmology, for example. And in particular, we show that you can complement the Friedman dynamics in some regime with an earlier dynamics, which is of a bounce type. So we see, you can, you have a bouncing cosmology rather than a singular cosmology. And the other thing we have seen in some models is that we get also a microscopic explanation, you could say, of the late time accelerated expansion. Because in our model, it comes out directly from the interactions of the field theory, of the quanta of the field theory. So let me put it simply. What we try to extract is, what we try to get is a correspondence between the hydrodynamic approximation of these quantum gravity models and effective cosmological equations. Now, whether the effective cosmological equations we get from any given model are interesting or not, well, depends on how they look like. You may get some modified cosmological dynamics that is ruled out already by observations or inconsistent for some other reason. But what we want to do is cosmology. We want to extract some effective cosmological dynamics that is embedded in a fundamental quantum gravity formalism. so that in principle we can compute quantum corrections, improve the approximations, and so on.
Thank you so much. Thank you.
You're welcome.
Okay. More questions, please? If there is no more questions, let's thank the speaker again. Thank you very much. Daniel, thank you.
Thank you.
Yes. And
Yes, thank you very much.
everybody, maybe I would like to make some small announcement. And by the way, next week we start our garography conference at Steklov Mathematical Institute. We will send for all people the announcement. Please, all of you are invited, for sure. Okay, thank you.
Thanks. And Daniel, it would be great if you can send slides.
Sure, I will send you the slides.
Okay.
Thank you again. Bye-bye.
Thank you very much.
Bye.
মাথা দিন হরিণ বুঝিত